In computer science, particle swarm optimization is a computational method that optimizes a problem by iteratively trying to improve a candidate solution with regard to a given measure of quality. PSO optimizes a problem by having a population of candidate solutions, here dubbed particles, and moving these particles around in the search space according to simple mathematical formulae over the particle's position and velocity. Each particle's movement is influenced by its local best-known position but is also guided toward the best-known positions in the search space, which are updated as better positions are found by other particles. This is expected to move the swarm toward the best solutions. PSO is originally attributed to Kennedy, Eberhardt and Shi and was first intended for simulating social behavior, as a stylized representation of the movement of organisms in a bird flock or fish school. The algorithm was simplified and it was observed to be performing optimization. The book by Kennedy and Eberhardt describes many philosophical aspects of PSO and swarm intelligence. An extensive survey of PSO applications is made by Polly. PSO is a meta-heuristic as it makes few or no assumptions about the problem being optimized and can search very large spaces of candidate solutions. However, meta-heuristics such as PSO do not guarantee an optimal solution is ever found. More specifically, PSO does not use the gradient of the problem being optimized, which means PSO does not require that the optimization problem be differentiable as is required by classic optimization methods such as gradient descent and quasi-Newton methods. Algorithm. A basic variant of the PSO algorithm works by having a population of candidate solutions. These particles are moved around in the search space according to a few simple formulae. The movements of the particles are guided by their own best-known position in the search space as well as the entire swarm's best-known position. When improved positions are being discovered, these will then come to guide the movements of the swarm. The process is repeated and by doing so it is hoped, but not guaranteed, that a satisfactory solution will eventually be discovered. Formally, let f(n) be the cost function which must be minimized. The function takes a candidate solution as argument in the form of a vector of real numbers and produces a real number as output which indicates the objective function value of the given candidate solution. The gradient of f is not known. The goal is to find a solution A for which f for all B in the search space, which would mean A is the global minimum. Maximization can be performed by considering the function h equals f instead. Let S be the number of particles in the swarm, each having a position n in the search space and a velocity v(n). Let π be the best-known position of particle I and let G be the best-known position of the entire swarm. A basic PSO algorithm is then, for each particle I equals 1, s do initialize the particle's position with a uniformly distributed random vector, (u), where below and above are the lower and upper boundaries of the search space. Initialize the particle's best-known position to its initial position. Π if less than f, update the swarm's best-known position. G π initialize the particle's velocity. v(u), until her termination criterion is met. Repeat. For each particle I equals 1, s do. For each dimension d equals 1, n do. Pick random numbers. Rp, Rg(u) update the particle's velocity. Phi, d omega phi, d plus phi p Rp plus phi g Rg update the particle's position. Shi plus phi if less than f, do. Update the particle's best-known position. Pi if less than f, update the swarm's best-known position. G pi. Now G holds the best-found solution. The parameters omega, phi p, and phi g are selected by the practitioner and control the behavior and efficacy of the PSO method. See below. Parameter selection. The choice of PSO parameters can have a large impact on optimization performance. Selecting PSO parameters that yield good performance has therefore been the subject of much research. The PSO parameters can also be tuned by using another overlaying optimizer, a concept known as meta-optimization. Parameters have also been tuned for various optimization scenarios, neighborhoods and topologies. The basic PSO is easily trapped into a local minimum. This premature convergence can be avoided by not using the entire swarm's best-known position G but just the best-known position L of a subswarm around the particle that is moved. Such a subswarm can be a geometrical one, for example, the m nearest particles, or, more often, a social one, i.e., a set of particles that is not depending on any distance. In such a case, the PSO variant is said to be local best. If we suppose there is an information link between each particle and its neighbors, the set of these links builds a graph, a communication network. That is called the topology of the PSO variant. A commonly used social topology is the ring, in which each particle has just two neighbors, but there are many others. The topology is not necessarily fixed, and can be adaptive. Inner workings. There are several schools of thought as to why and how the PSO algorithm can perform optimization. A common belief amongst researchers is that the swarm behavior varies between exploratory behavior, that is, searching a broader region of the search space, and exploitative behavior, that is, a locally oriented search so as to get closer to a optimum. This school of thought has been prevalent since the inception of PSO. This school of thought contends that the PSO algorithm and its parameters must be chosen so as to properly balance between exploration and exploitation to avoid premature convergence to a local optimum yet still ensure a good rate of convergence to the optimum. This belief is the precursor of many PSO variants, see below. Another school of thought is that the behavior of a PSO swarm is not well understood in terms of how it affects actual optimization performance, especially for higher dimensional search spaces and optimization problems that may be discontinuous, noisy, and time-varying. This school of thought merely tries to find PSO algorithms and parameters that cause good performance regardless of how the swarm behavior can be interpreted in relation to e.g., exploration and exploitation. Such studies have led to the simplification of the PSO algorithm, see below. Convergence in relation to PSO. The word convergence typically refers to two different definitions. Convergence to a local optimum where all personal best P or, alternatively, the swarm's best-known position G, approaches a local optimum of the problem, regardless of how the swarm behaves. Convergence of the sequence of solutions has been investigated for PSO. These analyses have resulted in guidelines for selecting PSO parameters that are believed to cause convergence to a point and prevent divergence of the swarm's particles. However, the analyses were criticized by Pedersen for being oversimplified as they assume the swarm has only one particle, that it does not use stochastic variables and that the points of attraction, that is, the particle's best-known position P and the swarm's best-known position G, remain constant throughout the optimization process. However, it was shown that these simplifications do not affect the boundaries found by these studies for parameter where the swarm is convergent. Convergence to a local optimum has been analyzed for PSO and it has been proven that PSO needs some modification to guarantee to find a local optimum. This means that determining convergence capabilities of different PSO algorithms and parameters therefore still depends on empirical results. One attempt at addressing this issue is the development of an orthogonal learning strategy for an improved use of the information already existing in the relationship between P and G, so as to form a leading converging exemplar and to be effective with any PSO topology. The aims are to improve the performance of PSO overall, including faster global convergence, higher solution quality, and stronger robustness. However, such studies do not provide theoretical evidence to actually prove their claims. biases. As the basic PSO works dimension by dimension, the solution point is easier found when it lies on an axis of the search space, on a diagonal, and even easier if it is right on the center. One approach is to modify the algorithm so that it is not any more sensitive to the system of coordinates. Note that some of these methods have a higher computational complexity where n is the number of dimensions that make the algorithm very slow for large-scale optimization. The only currently existing PSO variant that is not sensitive to the rotation of the coordinates while is locally convergent has been proposed at 2014. The method has shown a very good performance on many benchmark problems while its rotation invariance and local convergence have been mathematically proven. Variants. Numerous variants of even a basic PSO algorithm are possible. For example, there are different ways to initialize the particles and velocities, how to dampen the velocity, only update pi and g after the entire swarm has been updated, etc. Some of these choices and the possible performance impact have been discussed in the literature. Hybridization. New and more sophisticated PSO variants are also continually being introduced in an attempt to improve optimization performance. There are certain trends in that research. One is to make a hybrid optimization method using PSO combined with other optimizers, e.g., combined PSO with biogeography-based optimization, and the incorporation of an effective learning method. Alleviate premature. Another research trend is to try and alleviate premature convergence, e.g., by reversing or perturbing the movement of the PSO particles. Another approach to deal with premature convergence is the use of multiple swarms. The multi-swarm approach can also be used to implement multi-objective optimization. Finally, there are developments in adapting the behavioral parameters of PSO during optimization. Simplifications. Another school of thought is that PSO should be simplified as much as possible without impairing its performance, a general concept often referred to as Occam's razor. Simplifying PSO was originally suggested by Kennedy and has been studied more extensively, where it appeared that optimization performance was improved, and the parameters were easier to tune and they performed more consistently across different optimization problems. Another argument in favor of simplifying PSO is that meta-heuristics can only have their efficacy demonstrated empirically by doing computational experiments on a finite number of optimization problems. This means a meta-heuristic such as PSO cannot be proven correct, and this increases the risk of making errors in its description and implementation. A good example of this presented a promising variant of a genetic algorithm, but it was later found to be defective as it was strongly biased in its optimization search towards similar values for different dimensions in the search space, which happened to be the optimum of the benchmark problems considered. This bias was because of a programming error, and has now been fixed. Initialization of velocities may require extra inputs. A simpler variant is the accelerated particle swarm optimization, which does not need to use velocity at all and can speed up the convergence in many applications. A simple demo code of PSO is available. Multi-objective optimization. PSO has also been applied to multi-objective problems, in which the objective function comparison takes Pareto dominance into account when moving the PSO particles in non-dominated solutions are stored, so as to approximate the Pareto front. Binary, discrete, and combinatorial PSO. As the PSO equations given above work on real numbers, a commonly used method to solve discrete problems is to map the discrete search space to a continuous domain, to apply a classical PSO, and then to demap the result. Such a mapping can be very simple or more sophisticated. However, it can be noted that the equations of movement make use of operators that perform 4 actions, computing the difference of 2 positions. The result is a velocity. Multiplying a velocity by a numerical coefficient, adding 2 velocities, Applying a velocity to a position. Usually a position and a velocity are represented by n real numbers, and these operators are simply asterisk, plus, and again plus. But all these mathematical objects can be defined in a completely different way, in order to cope with binary problems, or even combinatorial ones. One approach is to redefine the operators based on sets. Applications. Optimization of hydrocarbon field development planning. Many of the optimization problems in science and engineering involve nonlinear objective functions. Particle swarm optimization has been applied for optimization of oil and gas field development planning. Individualized modeling. Individualized modeling is a computational technique that models a problem by trying to achieve an optimal model with regard to a specified input data or query.